All right, this is the second part of the tutorial on complexity and algorithmic game theory. And we're switching contexts for this talk, and we're talking about mechanism design. Okay? So I'm going to present some beautiful results that have been developed when you look at mechanism design from a computational perspective. So the plan of the talk is these 4 topics, and it doesn't make sense to go through them before I actually give you the sort of like motivation for the talk. So let's go back to our well-known and loved Vickrey Auction. So the setting is you have n bidders and 1 object. Each of the bidders or buyers has a value vi for the object, and these values are private. The item can only go to 1 of the bidders. You cannot split the item. And your goal is to allocate the item to the buyer who values it the most. So the well-known Vickrey Auction achieves this goal even without knowing the private values of the bidders, and it works as follows. You ask bidders to submit bids to the auctioneer. A priori, you cannot enforce that what they're going to say is the truth. Despite that, you treat these bids as representative of bidders' true values for the item. You select the largest one and give the item to that buyer, and you charge him the second highest bid. Now, the claim, it's an easy claim to prove. It's in the best interest of everybody to report the truth. Thereby, the auctioneer's goal is implemented through this auction. All right, so I'm sure everybody's familiar with the auction. And the cool thing is it generalizes, okay? And the running example in this talk is going to be the combinatorial auction setting, where I'm going to have n bidders. Think telecom companies. I'm going to have a set of m non-identical items. Think licenses for broadcasting. And each bidder has a potentially complex valuation function mapping bundles you can give them to reals. The constraints are, again, that each item can only be given to 1 bidder. And an allocation is any partition of the items to disjoint sets, where Si represents the bundle that goes to bidder I. Sometimes you can also allow throwing away some items, not allocating them. Right, so there are many different allocations, and our goal is to choose one that maximizes the total sum of values for the allocation, without knowing the true valuations of bidders a priori. And as I said, and you probably are all familiar with, the Vickrey Auction generalizes to this setting. It has a similar form. You ask bidders to report their functions now. Okay, so to report you the whole function, you choose a partition that maximizes the reported welfare, and there is a way to charge prices to make sure that the reports are the truth. Hence, your optimization problem is really optimizing what it should be optimizing. Okay, now there are obvious questions with this format of an auction. First one is, how are valuation functions communicated to the auctioneer in the first step? So a valuation function, if it's arbitrary, requires a lot of numbers to be specified. You have to give 1 number for every possible bundle. And even if there is some succinct way you can communicate your valuation to the auctioneer, the second step could be hard, right? So you're trying to choose among exponentially many allocations, the best one, the one that optimizes welfare, and this could be a hard problem. A very easy example is maybe bidders are single-minded. Each of them wants to get the whole neighborhood of a node in a graph. And say you have 1 bidder per node of the graph. Now, choosing even if you know the values, you know which neighborhood each bidder wants, choosing the best amounts to solving max independent set. So that's a hard problem, right? So So these are the obvious questions that arise when you want to follow this format, right? And sort of like the theme in this talk, at least in the beginning, will be to go around these two obvious problems. All right. So how can we reduce communication? Well, one obvious approach is to say, okay, so assume the bidder valuations are not arbitrary, but they have structure. How can a bidder maintain 2 to the m numbers in his mind anyways? Right? How can he be described by so many numbers? So chances are there is some succinct description of the valuations, and only target mechanisms that work with succinct valuations from some class that's rich enough to express reasonable bidders. Now the only roadblock then with running VCG is the computational step. The other approach to reducing the communication is resort to indirect mechanism. There are two standard approaches. So you can, the auctioneer, instead of asking the bidder to communicate his valuation in the first step, he can interact with him, asking him queries of the form, what's your value for a particular bundle? Or given these prices for the items, which bundle would you go after? Okay, so these are the standard approaches to getting around problem one. And I want to dwell a bit on the second approach and see what's happening once you want to design mechanisms that make queries to the bidders. And I'm going to augment my running example, which was an arbitrary combinatorial auction setting, with the assumption that bidders are not arbitrary, but they're submodular. What that means is that for every bidder, his valuation function satisfies this decreasing marginal returns property, which says that if you consider two bundles, S and T, where T contains S, then adding an extra item to the smaller bundle increases your value more than if you added it to the bigger bundle. That's what it says. All right. So here's an interesting algorithmic result. Due to von Drack, consider the running combinatorial auction setting with the assumption that everybody's functions are submodular. If you have access to the true, if you can, if you have query access to the true valuation functions, right? There are no incentives. This is an incentive-free claim. If you have access to the true valuation functions, then you can, in polynomial time, in both number of bidders and items, you can achieve a constant fraction of the optimal welfare. Okay? Now the question is, what happens if you introduce incentives? Right? If when you ask a bidder about his value for a particular bundle, he may strategize as to what answer to give you. It turns out that once incentives are introduced, all bets are off. Meaning, for instance, here's an example result. If a deterministic mechanism makes value queries to a bidder and wants to guarantee a very tiny fraction of the optimal revenue, which scales with the number of items, this is not a good performance. This is really bad, okay? So, but the claim is that if you have a mechanism that guarantees at least 1 over square root m, basically, fraction of the optimal revenue, welfare, then it must make exponentially many queries to the bidder. Okay, so having value access to the valuation functions, doing indirect mechanisms of this form is not going to help you. Right? You're going to lose a lot of welfare if you follow that approach. And okay, so this is restricted to deterministic mechanisms, but there are results, covering randomized mechanisms with a bit weaker bound, but this is already pretty bad. And also results that even cover any type of communication with a bidder. All right. So, and these are some example results. There is a long line of research that actually studies this problem. But the punchline is that there is a clear separation between what you can do if incentives are not involved, and what happens in the strategic world. Okay, so if people can strategize, then all bets are off. Okay, so you cannot get push always constant factor approximations from the algorithmic world to the strategic world. Right, and sort of like the punchline is truthfulness, communication, and approximation are at odds with each other, and we need more technology to understand what's going on. And I'm going to mention some of that technology. Now let's go back to the other problem, the conflict between truthfulness and computation. What if the valuations of the bidders can be described succinctly, so there's no issue with communication? Again, things aren't good in general. So even in settings where each bidder's valuation can be succinctly described with polynomial in the number of items communication, still you cannot get mechanisms that guarantee a constant fraction of your welfare. Okay, these are two example results. In fact, there is a long line of research that started with, I believe, a paper by Christos, Sapira, and Singer, which actually made this claim, but other papers that sharpened the claim, that separates the problems that can be approximated to a constant factor in polynomial time in the incentive-free world versus those that can be approximated in the strategic world. So in Christos' notation, the class of problems that can be constantly approximated, called APX, is different than APX to the IC. So if you consider incentives. Cool. Yeah.
Is it not for the public project problem, not the combinatorial?
Not so. The first one is for the public project problem. The rest, I believe, are for the combinatorial auction settings. Right. So this is what's going on with the conflict of incentives, computation, and communication. And it turns out that the world looks much better if you become a Bayesian. And so it turns out that Bayes can come to the rescue to rectify this picture a little bit. And let me tell you what's going on in the Bayesian setting. So for this part, I'm going to assume the same setting, combinatorial auction setting. Except now I'm going to also assume that for every bidder, we know a distribution Fi from which the valuation function is drawn. Right? And in fact, to leave communication issues aside, I'm going to consider an explicit setting. Namely, I'm going to assume that A is the set of all possible allocations that the designer can choose from. And I'm going to represent every valuation function explicitly, the value for each possible allocation. And I'm also going to assume that each Fi has finite support and see what how far I can go with an explicit representation of valuations like this one. Since I have now a distribution Fi, the new goal is to design a mechanism that optimizes expected welfare in Bayesian Nash equilibrium. Let me explain the terms. Expected means that I have to take expectation with respect to the FIs, the distributions from which bidders' valuation functions are drawn from. The randomness in the strategies used by the bidders when they interact with the mechanism, and the randomness that the mechanism may use as a tool to improve the welfare. And Bayes Nash equilibrium, I'm only going to say it's the right generalization of Nash equilibrium for this setting, which is an incomplete information setting with distributions. Now here's what. Any questions about the setting? Yes.
You're not restricting yourself to IC?
No, I'm gonna look at Bayesian IC.
Okay, Bayesian IC still. The way you've said here is not necessarily.
Okay, so for the upper bounds, I'm gonna get Bayesian IC. For some lower bounds, I'm gonna talk about any possible mechanism. So, right? So I'm not cheating. Okay. Right. So for any intractability result, I'm not going to assume that it has to be IC. For positive results, I'm going to provide Bayesian IC. So here's what's happening. Once you go to a Bayesian setting, cool papers by, among others, Jason, say the following. So suppose that the auctioneer has an algorithm which, given known valuation functions, V1 through Vn, would output an allocation that is achieving an alpha fraction of the optimal welfare. Okay, that's a tool that the auctioneer may have. It's an algorithm that, if people weren't strategic, would guarantee an alpha fraction of the optimal welfare. Now, the claim is that even if agents are strategic, all right, for any epsilon you desire, you can convert this algorithm to an algorithm that's robust to the strategic behavior of agents, and the guaranteed welfare is the same fraction of the optimum, except you're losing an epsilon, which you can tune to 0 by paying running time that scales a polynomial in 1 over epsilon. Right, so this is a result that converts an algorithm that works in the incentive-free world to an algorithm that works, that's robust to incentives, and is approximation preserving. Namely, if your algorithm gets, say a half of the optimal welfare without incentives, you're going to get the same fraction with incentives. And in some sense, this result represents an interesting sort of aesthetic for designing mechanisms. Before I get to that, what this result really means in the previous notation is that the Bayesian version of the same class is actually essentially equal to the Bayesian version of the same class to incentives. Right. So, but coming back to what I started saying, this result represents an interesting aesthetic for the design of mechanisms. And that aesthetic is inspired by reductions in complexity theory. And let me explain what I mean by that. So first of all, typically when we think of an algorithm, right, we think of an object that takes as input something and does some computation and produces the desired output of the computation. In a mechanism design world, the setting is the same, except some agents provide inputs to the algorithm. And unfortunately for the designer, the agents care about the computed output. Okay, so they have a keen interest on the output. And if it so benefits them, they may lie actually about the input they control to influence the output of the algorithm. Right? And a mechanism really is an algorithm that's robust to that strategic behavior. Okay, so now with this in mind, let's go back to the Vickrey auction, right? And in fact, Christos also mentioned this the other day. So let's think of the computation of the maximum of n numbers, which is a trivial algorithm we all did in, I don't know, first class in programming. But now let's change our perspective and back to my previous slide and assume that the inputs are strategic, and every agent I that controls input xi actually wants to be selected and has value xi for being selected. Okay. Now, if I run the trivial algorithm, every bidder is going to report plus infinity because they want to be selected. And one way to make a robust algorithm is to run Vickrey Auction, which is ask the strategic inputs to report how much they are, what they are, and after selecting the max, charging them as well to make sure that everybody says the truth. Right? So as Christos said, Vickrey Auction is the new max. Right? So back to my slide, mechanisms are algorithms that are robust to such behavior. And the question that arises is, and connects to sort of like the previous part of my talk, is how much more difficult is optimizing over strategic inputs compared to over honest inputs? And the dream would be to have a black box reduction from mechanism design to algorithm design for any optimization problem. What do I mean by that? So suppose we know an algorithm that works well on honest inputs. What we'd like to do is to sort of like come up with this other algorithm that interacts with agents and can also query this algorithm to get information maybe about the problem. And sort of like, after maybe several rounds of interaction with the agents and the algorithm, querying the algorithm to various inputs and getting the responses, produces an output in such a way that this whole scheme is robust to the strategic behavior of the agents. And if I interact with this algorithm just in an input-output way, without looking what's going on inside the algorithm, that's a black box reduction. So why would you like such a black box reduction between mechanism and algorithm design? Well, first of all, more is known, at least in the TCS community, about algorithms than mechanisms. So you would hope that some unsolved mechanism design problems would map to algorithmic problems that have already been solved. The other reason is that such reductions would allow a larger community to tackle important problems in mechanism design by leveraging their knowledge of algorithms, and without necessarily learning any game theory to do that. And in the end of the day, having such a reduction would provide a deeper understanding of mechanism design, giving information about what makes incentive difficult to deal with. Okay? So with this sort of like grand goal in mind, let me come back to this result and say that actually the reduction that they provide is black box. Okay? They don't need to understand the inner workings of the algorithm they're using. Okay? All they need is query access. Okay? So they want an API to an algorithm that solves the problem in an incentive-free world, and interacting with this algorithm just on an input-output basis, they can convert it to something that's robust. Okay? That's a very general result for welfare optimization in Bayesian settings. And there are some precursors in the non-Bayesian setting that I'd like to mention as well before I go on. So a beautiful result by Lavi and Swami shows that in a non-Bayesian world, in a non-Bayesian setting, if the welfare problem you're trying to solve can be written can be solved by a configurational P that would produce a fractional solution, together with a rounding algorithm, right? Then with black box reduction to the rounding algorithm, you can solve the same problem, get the same factor, approximation factor, in the strategic setting. Okay? This is not as general as this, but it says that if the welfare problem you're solving has a particular structure and can be solved by a particular type of algorithm, then with black box access to this algorithm, you can make it strategic, robust to strategic agents. Another result in the same vein is the following, that if your welfare problem is can be expressed as a packing problem, and sorry for the economists in the room if these are unknown words, I'm not giving the definition, but Let's say that I'm going to give you a flavor of these results if you don't know what these words mean. If your problem, incentive-free problem is a packing problem and can be solved to arbitrary approximation in polynomial time, then with black box access to the algorithm, this polynomial time approximation scheme, you can convert, you can solve the strategic problem to arbitrary approximation also in polynomial time. So these are just two examples of black box reductions between mechanism and algorithm design. Any questions so far? So all these results apply to welfare, and other objectives such as revenue are not well understood. With Yang and Matt, who are both here and will spend the semester here, we got in the Bayesian setting, we got a general reduction from mechanism to algorithm design for any optimization problem, as long as you put the right qualifications here. I'm going to show you the flavor of the reduction, but just an example corollary before I go on. As a corollary of this reduction, we get that there exist polynomial time computable revenue optimal mechanisms for additive bidders, which extends the celebrated paper of Myerson to multi-item settings. And in fact, it can accommodate various features like budgets, or in fact, can go beyond additive bidders and beyond the objectives of welfare and revenue that are well studied. Now, also, by using this basically purely algorithmic result, we also get structural information about the optimal auction. And I'm also going to give a flavor of what we get. But before I sort of present this result, let me give a pointer to the talk of Christos Jamos in the Complexity and Simplicity workshop, where he's going to talk about how you can use optimal transport theory to characterize the structure of the optimal auction even better, tighter. Okay? Or you can see a survey I wrote for the past SIGOM exchanges volume. In any event, let me give you the flavor of this reduction. And again, what I want you to have in mind is this picture, because now I want to state general. I want to state the mechanism design problem in the most general way, and relate it to a corresponding algorithmic problem and provide a reduction between the two problems. Okay, so I claim that a very general mechanism design problem looks as follows. You have some input set X and some solution set S, and you also have an objective function O. Now, the objective function O will get an n tuple of inputs together with a proposed solution, and will tell you how good the solution is for that n tuple of inputs. That's a general way to describe an optimization problem. This is going to be a mechanism design problem. So I'm not going to have the inputs directly, but I'm going to have access to strategic agents, 1 through n, such that each agent I knows the realization of the ith input. But this is private to him, and I don't know it. I'm going to have a distribution from which that input is drawn. So that makes the setting Bayesian. And what is interesting, and this captures the fact that the inputs are actually it's a mechanism design problem, so the inputs have a keen interest on the output of my computation. These inputs are both inputs to the function that I'm trying to optimize, but they're also functions themselves, right? And this is how much they like each solution. Okay, so that's a general way to phrase a mechanism design problem, right? So this is the auctioneer's, the designer's objective, that cares about the realized inputs of the bidders and wants to choose a solution, an allocation, for example, to maximize that objective, to make the score as high as possible. On the other hand, each input cares about the solution that the designer chooses, so this is also a function that tells you how much that bidder likes its solution. Does it make sense, the abstraction? Yeah.
Sometimes your designer might care about the expected value of the objectives. So you're looking at a part-wise thing, but in principle there could be trade-offs between the high value and some values of X.
That's true. So this is this. All right, so the goal of the designer is to optimize the expected objective value. And what I've written in this slide is that he wants to find a truthful mechanism. That's not necessary. Maybe you want a non-truthful mechanism, but really your goal is to optimize the expectation of your objective, where the expectation is over the distributions and anything else that's random in your setting. Okay? But I'm going to insist on truthful mechanisms just because it doesn't hurt me. But now, so this is a general way to abstract. This is a way to abstract a mechanism design problem. The corresponding algorithm design problem is basically the same, right? Except, so you have the same set X as an objective function, except now you know the inputs. You know exactly, sorry.
One more question.
Yeah.
Mapping you have what looks like a standard mechanism called notation, but we usually have some notion of individual rationality constraint as well as the set of compatibility. You've got keen interest.
Yes.
Is I guess the set of compatibility, but what kind of individual rationality constraint?
Same. So I actually do that as well. It's in here. I didn't want to. Yes. So you want to design a mechanism that where where agents will truthfully report their inputs, and also will come and participate in your mechanism. So all these constraints are here. I'm just abstracting them away.
The only reason I ask is because there are different versions of this will come in the literature. There's ex ante interim and ex post individual rationality. Will come to the mechanism.
Ex post.
Oh, ex post for every type.
Yes.
Okay.
But you can choose. If you want ex ante, I'm happy to accommodate. But or if you don't want individual rationality, I'm also happy to accommodate. But
I just like to know.
Yes. No, it's a good question. So, on the algorithm design side, the problem is the same, except now you know the inputs. So there's no question about what the inputs are. And what you want to do is you want to choose the solution S that optimizes how good that solution is for those inputs. All right? And what I'd like to get is a reduction from this problem to this problem. Because obviously, if you can solve this problem, you can definitely solve this problem because maybe the distributions are pointwise. Right? So this is a special case of this problem. Right? So maybe you just exactly know the valuation of everybody, the input of every agent. So if you're able to solve this problem, definitely you can solve this problem. Question is, if you have an algorithm for this problem, can you also solve this problem? Right? And I want to get a generic reduction from the left-hand side to the right-hand side. Yes?
About the intuition, is it in general true? Because it looks like you need something like the program is divisible, so that you need some assumption like so that if each player somehow optimize their strategy individually, they can reach some approximate optimal solution like that. You don't need because in this description you didn't mention any other assumption, right? So there is still looks very amazing without some intuition why this can always be.
I'll try to give, yeah. So in the next slide, I'll try to give some intuition about why this reduced. But first of all, let me say that such reduction doesn't exist. Okay. All right. So you would like to have this reduction, but it does not exist. This is a result by Chale, Morlik, and Lucier. Saying that, so maybe, sometimes you can solve this problem, but it will take you a lot of computation to use this algorithm to solve this problem. So this you cannot do. But what you can do is you can perturb this right-hand side a little bit. and make the reduction possible. So the perturbation that we propose is to change the algorithm design problem to have actually two objectives. One objective is the original objective. The other objective is a linear cost function. It's a welfare. Okay, so we take that objective from the mechanism designer, and we change it to the same objective plus welfare. Now, the input is, we have two inputs, okay? Inputs xi, like over here, but also inputs yi. So this is a well-defined problem now, right? So this is a well-defined algorithmic problem. It takes as input, XSO, two tuples of inputs, and wants to optimize the objective O plus welfare. So we change the problem on this side. Right? Now the X's come from the original set. The Y's come from the same set, the closure of that set under linear operations. That's why I have this plus minus here. All right? So this algorithmic problem is related to that, but it's not the sort of like the deterministic version of this problem, because I have changed my objective to add this this welfare term, if you want. Yes?
So what exactly is the difference between xi and yi?
So forget about what I've talked about and just look at this problem, right? This is a well-defined problem. It says I give you two tuples. It's just a function that takes 2n inputs instead of just n inputs, right? And the objective is the original one plus welfare, right? So if you look at this thing, it's a welfare function, right? Because you sum over agents, how much the agent likes the solution. So that's a welfare function. This function, it's whatever it is. It could be revenue, it could be welfare, it could be makespan, it could be whatever the designer is trying to solve.
So x plus is some sort of linear closure of x, so x lives in Rn or something? This was a set with, x was an abstract set.
Functions, so linear, yeah, so it's same set with linear closure.
Okay.
Yeah.
How do you define y sub I of s?
This is a space of functions, right? And this is the closure of that set under linear operations. So these are also functions. So this is well defined, right? So since this set contains functions, right? So yeah. Right, so, yes.
For completeness, so if x is for concreteness, if x is submodular evaluations, x plus minus is what?
It's not submodular evaluations, and that's important. Yeah, it is not.
What is it?
I don't know what it is. Yeah. But so if this is additive valuations, this remains additive valuations. This I can say, okay. But if it's, for example, submodular, this is not submodular because I don't know. Actually, it could be. I don't know.
The plus term is not really welfare, it's discriminatory welfare, anti-welfare. You could have minuses there. I dislike somebody, so I give him a negative.
Yes, so we call it virtual welfare. Yeah. So,
Is it like a Lagrangian of sorts? Like you're pushing the xi into the objection?
We're not doing that, but I believe there is a way to think about it this way. Yeah. So let me state the result. We obtain a polynomial time black box reduction for any objective that you care about from this side to this side. In other words, if you have an algorithm for this problem, then putting through our reduction, you can get a polynomial time mechanism for the original problem. And it's also approximation preserving. If you can only alpha approximate this, you can alpha approximate that. And the techniques are basically hinge upon two things. So one is using the power of the ellipsoid algorithm. The other part is to use Border's theorem that Jason talked about earlier today. And in fact, extend Border's theorem to multi-item settings. Okay, so I realize that this is an abstract theorem, and I want to instantiate what's going on in a very, very trivial setting. Yeah.
Is there an equivalence? Is it the case that?
Is it infinite leaf?
Yeah, it's infinite only. Yeah.
Not always, but not always. Yeah. So I want to instantiate this abstract setting in a very simple case that we already know how to solve. I'm going to have one item and bidders, and each bidder I will have some scalar now value that belongs to some set Vi and is drawn from some distribution Fi. Both the distribution and the set are known. The realized value of the bidder isn't known. So it's a Bayesian setting. And the goal of the auctioneer is to optimize revenue. And what I want to do is I want to formulate, so we know how to solve this problem. We can run Meyerson's auction. But what I want to do next is I want to formulate the problem as a combinatorial optimization problem instead of, I don't know, like doing analysis. Okay, so I'm going to assume that everything is finite. So the support of this thing is finite. One way to optimize over mechanisms is to actually optimize over allocation and price functions. So in the end of the day, a mechanism is a mapping that takes as input the reports of the agents and decides with what probability to give the item to each bidder. And it also takes a bunch of reports and decides how much to charge every bidder. Okay, so at the end of the day, finding the optimal mechanism is nothing but looking for the best allocation and price functions. Right, so the mechanism that I'm trying to find will ask bidders to report their values. Given the reports, it will allocate the item to bidder I with probability xi and charge him pi, and both of these are functions of the reports of everybody. Now I have to make sure that my mechanism is feasible, and that be guaranteed by this constraint, which says that no matter what the reports of the bidders are, if I sum the allocation probabilities, I don't exceed 1. I also have to make sure that bidders, I'm looking for a truthful mechanism, so I want to make sure that bidders are not going to misreport their values. And this constraint captures that because, okay, so the quantification is for all pairs of possible values for bidder I. And what's happening here is that bidder I takes an expectation over the values of the other guys. And he's interested in the probability that he's going to be allocated the item if he reports VI. In which case his expected value would be this, the product of the probability and his value. And he's going to be charged this price. Okay? And that both of these depend on the other people's report, and he's taking an expectation over them. He's comparing the expected utility with what would happen if he instead misreported his value and said VI prime. Okay? And what this constraint says is that for every possible values, he doesn't want to do that. Okay, that's the standard thing. So, and the expected revenue is can also be written as a linear function of my variable. So, in the end of the day, everything that I need to express my objective, which is the expected revenue, as well as the feasibility constraint and the incentive comparability constraints, they're all linear constraints in my variables. So this is an LP that I can solve. Okay, so finding the optimal mechanism is just an LP. But the issue is that this LP has too many variables, right? So I have a variable for I have two variables for every possible report by the other bidders. So if every bidder has t possible values, then the number of variables is exponential in the number of bidders, which is not something I can accommodate. So the proposal, an interesting proposal, used in the mechanism design literature, is to look instead, study interim allocation rules. An interim allocation rule is what Jason was talking about, except Jason described it in terms of quantiles, and I want to describe it in terms of values. So here's the definition. So the interim allocation to bidder I when he reports a particular value is the expected probability by which he's going to receive the item if he reports that value in expectation of what the other guys are going to say. Okay, that's all it is, right? And similarly, the interim price that bidder I is going to pay if he reports VI is the expectation over what the other guys are going to report of the price he's going to pay. Now, the motivation for this definition is that if we look at the second constraint, on this constraint, the Bayesian incentive comparability constraint, and take expectation through, right? We really recover the interim rule here, right? So if this expectation goes through here, I'll get the interim rule over here and the interim price over here. So this constraint really only cares about interim allocations and not ex post allocations, which are here. Similarly, the revenue only cares about interim prices, right? So the motivation for these two definitions is that at least these two constraints only care about the interim description of the mechanism. So taking expectations, what's going on here? Taking expectations through, these two constraints become just linear constraints in the interim rule. And really the only trouble with using this interim rule instead of the ex post rule is that the first constraint cannot be expressed easily in terms of the interim description of the mechanism. Right? So the first constraint says for every possible vector of reports, the sum of probability of allocation probability should not exceed 1 because I have one item. But this is hard to express in terms of the interim rules. Right? So I have to find a way to express this constraint in terms of the variables that I'm interested in. The reason I want to use these variables is that these have polynomial description in the size of my problem. Okay, so let's dwell a bit on this and look at an example. So suppose I have two bidders, and their values are drawn from this set. For bidder 1, ABC, uniformly randomly, and for the other bidder from the set DEF. So these are the two values, whether it's random in the two sets. Now let's try to see, okay, so somebody proposes the following interim allocation rule to us, and we want to decide if this is feasible. Namely, if there exists an ex post rule that induces this interim rule. Okay? So what do you say? Is it feasible or not? So it's not obvious whether it's feasible or not, but there's we can sort of like work our way through and see if it is. So for instance, we see a 1 here. This 1 says that if bidder 1 reports, if bidder 1's type is A, then no matter what else happens, no matter what this guy says, he has to get the item. All right, so whenever bidder 1 reports A, he has to get the item. Otherwise, this constraint would not be satisfied. Right? This constraint says that whenever 1 says A, he has to get the item with probability 1, no matter what the other guy says. So this is forced. Whenever the reports are A and anything, A has to win. Now, if I make this assumption, and I'm forced to make it, then there is a suspicious 2 over 3 over there. Right? Now, D has already consumed 1/3 probability against an A, so we better give him the item against B and C. So whenever the reports are B and C versus D, now D has to get the item. And now we make this constraint satiated. Okay, so these two are happy. Let's see about these other two guys. Well, since this is a 0, whenever we have B and F, we can comfortably give the item to B. And we get at least 1/3, right? Because this event happens with probability 1/3. And similarly, whenever we have C and E, we can give it to E. And now this guy, this is a 2. This guy gets also at least a third. But these guys require more, right? And we have to decide what happens when they appear against each other. And it turns out that to satisfy these two numbers, you need, in this case, to allocate the item with probability 1/2 to B and 2/3 to E, which is certainly not possible. So working our way through this example, it follows that it's infeasible to satisfy these constraints. Any questions about what happened here? Or the definition of interim rules? It's a bit hard to work your head around the interim rule because it has taken an expectation over what happens outside of this bidder. So that's what makes it hard. But this is already hard to do. Like, and we're lucky here because we had this one that helped us. We have issues.
Don't go to full screen.
Well, that's my family. Let's see. Okay. Yeah. So, all right. So, in the previous slide, oh, come on. Okay. In the previous slide, we were lucky because we had this one that forced our way through this example and these 2/3. But in general, it's hard to check if an interim rule is feasible. Right? So the question is there a easy way to check whether an interim allocation rule is feasible? And starting with border and follow-up papers, we got a very nice characterization of when an interim rule is feasible. Jason showed it in some way. I'm going to show it in another way. An interim rule is feasible if these constraints are true. So now let's try to read them. So we want that for any subset of the possible values of each of the bidders. So this is a collection of subsets of possible values. We want to have that this is smaller or equal than that. Now let's read this thing. So this sums over bidders, sums over values in the selected set, the probability that bidder i's value is vi, and conditioning on that, getting the item. So this thing is the probability that the item goes to some bidder whose value was sampled inside this set that we chose. On the right-hand side, that's easier to figure out, is the probability that there exists a bidder whose sampled value is inside the set. So clearly, if the rule is feasible, it must be that this is smaller or equal than that, right, for any selection of sets. What the theorem says is that this is an if and only if. Right? So this is Border's theorem. And you shouldn't be surprised by it if you know max-flow min-cut. And in fact, Jason's proof in the morning was a max-flow min-cut proof. But again, these are too many constraints, because if I were to add these constraints to my LP, I will have to take a for all every possible subset of types for every bidder. So there are too many constraints. And what Yang and I proved, and independently Ally et al., is that, in fact, you can choose. So we showed that you can choose a small subset of this constraint, and this suffices for feasibility. So now plugging these constraints to the LP I had before, I have a polynomial size LP, and I can find the optimal mechanism. That's basically how things get.
These constraints help you change variables, you're saying.
Exactly. If I didn't have these constraints, I wouldn't be able to express this as a linear constraint. But now I can. Of course, this was just single items. Yes?
So you used that additional linear social welfare term here, or that wasn't?
No, I didn't. I haven't shown you how this is used yet. I'll show a sketch in a little bit. But. So this is single item feasibility. And this was the workhorse in JSON stock. But it doesn't always work for multi-dimensional settings, multi-item settings. It was used in JSON to understand some multi-dimensional settings, but it doesn't work always. And just to give you like a hint about what's the difference between a general multi-dimensional setting and what Jason was talking about, consider these two settings. One is you have two bidders, two Mercedes cars that can be painted either red or blue. Versus you have two bidders and two cars. One is a Mercedes and one is a Lexus, and you cannot paint the Lexus to make it a Mercedes. So the difference between these two settings is that in this setting, the allocation rules are really single-dimensional. So you can use Border's theorem to design optimal multidimensional mechanisms. Right? So it's a multidimensional setting because bidders have different values for red and blue. Nevertheless, the allocation rule is single-dimensional because basically you have two Mercedes, right? And you can customize them after they're allocated. In this setting, you have a multidimensional allocation constraint. So this is not covered by Border and needs more technology. And the pertinent question is, okay, so you have to come up with some interim rule to describe even multidimensional settings. The question is what information you need to maintain in this interim rule. And the obvious approach is to generalize what I was doing in the single item setting. So what you can do is for every bidder I, for every possible now valuation for that bidder, because we're in a multi-item world, for any bidder I, and for every possible valuation function for that bidder, and for every item j, you can maintain in your interim rule the probability that item j is given to bidder I when he reports this valuation function. But this is the immediate generalization of the single item interim rule I was talking about. And the question that arises is this a good enough information to maintain in a multidimensional world? And as you probably guess, it is good only in very special cases. For example, additive or unit demand bidders. Because if a bidder is additive and he's summing the values of the items in the bundle you give him, then if you know the interim rule, you can exactly understand his expected utility, his expected value, because you can take an inner product of these probabilities with the value, with the vectors of values characterizing his additive valuation. But it's not true in general. So here's a trivial example. So suppose you have a bidder who wants a pair of shoes for $10, and he doesn't care about getting either a left or a right shoe. And consider two mechanisms, two allocations. One is you allocate both shoes to the bidder with probability I have, versus you allocate a random shoe to the bidder. Now, if you think about it, the interim allocation probabilities of these two allocation rules are exactly the same. But that's not enough information for the bidder to understand how good this interim allocation is for him, unless he sees the fully fledged allocation, ex post allocation rule. So if I'm committed to working in the interim world, I cannot get away with just maintaining marginal allocation probabilities of each item to the bidder. Yes?
So you have there additive/unit demand?
Yeah.
But this example would work equally well in unit demand. Like
Yes.
Yes, for shoes that there's no added value. And so
Right. Yeah.
what are you?
That's an excellent question, and maybe I shouldn't be saying that, but unit demand is easy to handle by pushing this constraint to the allocation rule. You can push it somewhere else, but you're right. But anyways, think additive.
It seems like what you need is a canonical interpretation of the marginal interpretation.
Yes.
Like as a bidder, I knew you were going to make it ex post in the way which is best for me.
Right. If it was clear to the bidder what these probabilities mean, if it was clear, basically you want a way to go from interim allocation probabilities to ex post probabilities over bundles. If you have a canonical way to do that, you're good. Of course, you could be more explicit and maintain interim allocation probabilities over all bundles, but that's too expensive. And instead what we do is we are actually not literal about allocation rule. We forget about allocation probabilities. And really what we maintain is this funny thing that we call interim swap value function, which basically says, in expectation of what the other bidders are doing, what would be my value if my real valuation function was VI, but instead I set VI prime to the mechanism. So this is just an arbitrary definition that is not nothing to do with an allocation. It's, the allocation maybe is very implicitly hidden behind this. But what we show is that you can actually write a polynomial size LP in terms of these guys, and you can solve it to get a mechanism. So this is at a very high level what's going on. Coming back to this picture, basically what's going on is that,
Can we ask you something?
yeah.
Sorry, but I mean, you clearly wrote at least exponential size LP right now down.
Where?
Phi I, VI, VI prime. There are many VIs and many VI primes, so you're having like
Yes.
many variables. So
So I'm working, you're right. So I'm working in the setting I mentioned at the beginning. The distribution Fi has finite support, and that's part of my input. Right? I'll tell you in a second. Okay, so the importance of this result is to get rid of the exponential dependence in the number of bidders, which is not here. Yes?
Does this way to write things instead of interim allocation rules allow you to handle correlation?
Yes, we can do. We have some results about that. Yes, we cannot. We don't.
More complex than just using this. Like, is it?
So the answer to you can write something like this to handle correlation. We have not really seen if you can use it to get mechanisms, but you can use this approach to handle correlation. But this shouldn't be with respect to yourself, but also other bidders, right? So there has to be something about other bidders in the interim rule. So, coming back to this very high-level picture, here's the high-level sketch of the proof. You write a polynomial size LP using these interim swap values. Again, your issue is that feasibility is hard to check. It's hard to understand, given an interim swap value function, whether there is a mechanism that induces that swap function. And what we want to do is develop a separation oracle for this problem, so that we push it into an ellipsoid algorithm to solve our LP. And it turns out that if you study this problem really, really hard, the separation oracle you need, the algorithmic problem you face to develop this separation oracle is exactly this thing. So that's how this problem gets related to mechanism design, right? So you want to solve this mechanism design problem. You write it as an LP. You have to make the LP succinct, so you resort to using these interim objects. Now you have to be able to tell if an interim object is feasible. And if you work hard, you realize that the algorithmic bottleneck to solving that problem is exactly this problem, which looks similar to that. So this is how we got the reduction. And an important byproduct is that we not just get a polynomial time computable mechanism, but we get some structural understanding of the mechanism. So in this setting of revenue optimization, with multiple items and say unit demand bidders, the mechanism looks suspiciously similar to Meyerson's auction. The mechanism is to ask bidders to report their value for each of the houses. We then transform these reported values to virtual values using some mapping from values to virtual values. And then after that, we find a max weight allocation, like Myerson does, charging prices to make the whole scheme truthful. So this is, if you're familiar with Myerson, this is very similar to Myerson. The difference is that we don't understand the virtual transformations very well. They're output by the ellipsoid algorithm, and they're randomized. In the world of, with Alan Deckelbaum and Christos Gamos that I mentioned, we provide a partial answer to how these transformations look like. And let's see. So for the last sort of like 2-slide part of my talk, I'm coming back to computation and asking the question, does Bayesian, so Bayesian assumption helped us in getting these reductions from mechanism to algorithm design. Question is, does it help us also reduce communication? We've already seen that in a non-Bayesian world, these things are in conflict. So question is, does Bayes help? So a result also mentioned by Tim on Monday in this vein says that consider a Bayesian combinatorial auction setting with sub-modular bidders. And instead of doing anything complicated like VCG, suppose you just run simultaneous first price auctions or simultaneous second price auctions. The result is that in Bayes-Nash equilibrium, these auctions will give you a good fraction of the optimal revenue. Right? So the Bayesian assumption helped here as well. So you got mechanisms that require minimal communication with the bidders and guarantee a constant fraction of the optimal revenue. Of course, the world is not exactly as good as it looks because there are computational lower bounds saying that the Bayes-Nash is good, but it's actually hard to find in some settings. Nevertheless, and this is another very nice result in this area, there are ways to go around it. So Feldman, Gravin, and Lucier very recently have shown that there exists a sequential posted price mechanism that guarantees a half fraction of the optimal revenue in a Bayesian setting. And this mechanism is basically trivially truthful. So bidders come after the other, one after the other, and select their best bundles out of the remaining bundles, subject to the prices that are there. So Bayes really helps in communication. But this sort of like is an interesting point to mention a very interesting simplicity versus complexity trade-off that is important for mechanism design, and in fact is it's part of the title of the second workshop this semester. So clearly, if you have a simple mechanism with obvious equilibria, this is a great thing, okay, to use. But what if you can have this thing? Then what is it better? Is it better to have a complex mechanism with obvious Bayes-Nash behavior or a simple mechanism with intractable equilibria? I'm not going to answer this question, but you're invited to our workshop in October to study this problem. So in conclusion, standard mechanism may not be implementable when you introduce computational and communication constraints. And communication and computational complexity provide tools to study mechanism design under these considerations. And in fact, very beautiful results have come out of trying to prove intractability results for mechanism design. On the other hand, in Bayesian settings, you can bypass a lot of these lower bounds. I mentioned a general mechanism to algorithm design reduction with Yang and Matt. And I also mentioned how Bayesian setting can be leveraged to go around the communication lower bounds. And I think there is some interesting work to be done here because this is a singular result that I know in this setting. And with that, thanks a lot.